thank you the organizers for this kind of opportunity, and thank you for the person, the man who introduced me for the nice words. So, yeah, Janardhan sir, Seshu sir, thank you for the invite, okay, and for the principal sir for the support. So, today I will be just speaking about hyperspectral signal. First we need to understand what is image. I think all of you will have a nice idea of what image is. Am I audible?
First
I'm audible now? Yes.
dot లేకుండా ఇంకోటి ఫస్ట్
Yeah. So I hope all of you have an idea of what images are.
వెనకాల ఉంటుంది.
So you can see, I think most of you are from the electronics background. You can correct. Yeah. So all of you have an idea of signal better than me because I am from computer science background. You are from electronics background. Of course, you have a better idea what's a signal. So if I say what's a signal, it's just the variation of amplitude with respect to time, right? Audible? Yes. So you can draw a signal like this, right? So it's a variation of amplitude or variation of energy in time. So amplitude versus time. So signal. So if I say that image is also a signal, how many of you will agree? Image is a signal, yeah. So how you can say that image is a signal? Yeah. So what is varying in this two dimension? Yeah. Pixels are the intensity values. Instead of amplitude varying with time, here the pixel values or the amplitude itself is varying with x and y. So you have two dimensions, that is, instead of time, here you have amplitude and x and y. So your amplitude is varying with respect to x and y coordinates. So that's why we call images as a two-dimensional signal. I think this is getting stuck, but I think am I audible? Yes. So you can see that if you zoom to a pixel level, zoom an image, we can see like this, right? So these are the pixels. So these are the smallest elements in an image, beyond which we cannot go. So that means each of these pixels will correspond to some values. So you can see this is the image, so this is the pixel value, so this is the actual value. So an image you can represent as a matrix. So the idea is that you will have this, x and y. So this is a two-dimensional signal now. So like your signal is varying with respect to time, here it's varying with respect to x and y. For example, at this particular time this was the amplitude. So at this particular x and y this is the amplitude. At this particular x and y this is the amplitude. That means the value of the amplitude is here. So at 0, 0, x equals 0, y equals 0, this was the amplitude or this was the value. X equals 0, y equals 1, this is the amplitude, right? So that means I can say that this is a two-dimensional signal where the values varies with respect to x and y. So we can say that image is nothing but a signal, two-dimensional signal. So now we have to have some basics of images, right? We can have black and white images and grayscale images. We are not discussing about color images yet. So first, black and white and color and grayscale images. What's the difference? See, black and white means you have only two colors, white or black, only two colors. But in childhood, you may have drawn pictures. How children will draw pictures. If you ask him to draw, if you give him a pencil and ask him or her to draw a picture of a person, what he will do? He will have different shades of grey. The black shades, the higher shades will be for the hair. Wherever black portions, he will shade it very high. So it's not color, but still he can use different shades of grey to convey some message. So you can see these two images. Here it's a black and white image. I have only two colors, either black or white. But here you can see it's more different shades of grey I am using. So that means how many levels I can have. So here I can have only two levels, 0 or 1. Here I can have many levels, but still it's not a color image, it's still a grayscale image. So this type of images we call them as grayscale images. So So that means, so how many levels I can have? See here, it's a binary image, I can have only two levels, 0 or 1. Now if I will say that, I am using only one bit to represent this pixel. We have seen the pixels. See, if you have any concerns on this, please do ask, because we are building on this to move towards hyperspectral and signal processing. Okay. So I think most of you know these stuff. We are just refreshing it. So this here you can see that we are representing one pixel, right? There are some values for the pixel. So how many bits you need to represent a pixel, that determines how many levels you can have. I hope it is clear. That means if it is black and white, you can represent, one bit is used to represent one pixel, so you can have only two values, that is 0 or 1. If you have 2 bits to represent one pixel, then how many values you can have? 0 0, 0 1, 1 0, 1 1. So that means 0 to 3. So if I have only one bit for representing a pixel, I can have two values. If I have 2 bits, I can have 4 values. That means here I can have 0 to 1, here I can have 0 to 3. Here I can have 0 to 3. So that means if I have 1 bit, I have only 2 values, 2 bits means 4 values, 3 bits means 8 values. So that means 2 raised to n. How many bits I am using, that many levels I can have. So this is called the radiometric resolution of an image. Means how many bits are you using to represent a particular pixel, that denotes how many levels you can have. For example, if I say that you have say 5 bits, so you can have levels from 0 to 32, sorry 0 to 31, so total 32 levels you can have. So that is where this radiometric resolution plays a role. That means the levels, how many levels you can have. So we are just discussing about grayscale images. These are not color images. So one is black and white image, another one is grayscale image. We started with the notion that this is a two-dimensional signal and we can have color and we can have grayscale and black and white images. Black and white means it's a binary. It's a type of grayscale image where you have only 2 levels or 1 bit you are using for representing one pixel value. As you use more and more bits for representing a pixel value, you can have more and more levels. That means when you have more and more levels, you can draw very beautiful pictures. So that means you can represent more data when your radiometric resolution is more. You can see here. See, this is having 1 bit radiometric resolution. This is having say more bits of radiometric resolution. So you can see the difference here itself. So now moving on to color images. Suppose I have 3 cameras here. One camera will take your photograph and it will give me a grayscale image for the red wavelength or red electromagnetic spectra coming from you. How we are taking photograph, how you are able to see me, because there is a source of energy which may be the sun or these lights. That source of energy is hitting on me and then it is coming back to your eyes. So that means the waves reflected by me is getting onto your eyes. That is how you are able to see me. So why this shirt is appearing in this color? Because this color is being reflected by the material of this shirt. So that is why you are able to see this shirt in this color. If someone is wearing a red shirt, what does it mean? Means that material is so made that it can reflect the red color only and absorbs all the other colors. So if I am using a camera to capture all the red colors, another camera for capturing all the green colors, another camera to capture all the blue colors, I will get 3 grayscale images. I hope it is clear. I will get 3 grayscale images, and when I combine them together, I will get a color image. So this is how our eyes also perceive things. So that means there is 1 grayscale image for red, 1 grayscale image for blue, and 1 grayscale image for green. So if I am wearing a red shirt, my grayscale image for that red color will be having maximum value. Maximum value means, see, if I have only one bit, it is 0 and 1. If I have 5, it's like 2 raised to 5, right? So 0 to 31. So 31 will be the rightmost, that means white one will be 31 and dark one will be 0. All the other will be in between. See, 0 means white, 1 means black. If I have values from 0 to 255, 255 is the white and 0 is the black one, and all the other variations I have in between. So that said, when I have one image red, one image green and one image blue, when I can combine them together, I get something like an RGB image or the color image. This is the image that we usually see. So this is color image. So one color image is made up of different grayscale images. So this is, so that said, so when you see an image, it's a stack of different bands. One band is a red band, green band, blue band. So usually your color images will be having 3 bands or 3 grayscale images, one for red, one for green and one for blue. So each band will be one grayscale image, that means each band will be a 2-dimensional signal, and you can locate a pixel using that location. So this is how the whole image formation lies. So what is our problem? Our problem is that we can sense only these 3 regions of the electromagnetic spectrum, that is red, green and blue. We cannot sense the other regions of the electromagnetic spectrum. I hope all of you remember electromagnetic spectrum. So it's having a lot of wavelength ranges, but we are not able to sense the other wavelength ranges. We can only sense red portion, green portion and blue portion. So yeah, and one more thing I just want to underline here is, this is usually if you have multiple signals. You can see here, this is one signal, this is another signal, this is another signal, all of them combine to form this signal. Okay, I hope it is clear. So this is, this all of them added together in some weighted combination to give this particular signal. So if I want to represent this signal, see, usually you all know that we are representing signals in time amplitude domain, but if you want to represent it in frequency and that amplitude strength domain, then what you do is, which frequency was composing this signal, what was its strength, and that frequency, and that frequency, and that frequency. So here you can see that 3 of these waves are combined together. So these are the base frequencies which gave rise to this particular the signal. So that said, you can use this as the base signal or the basis. So what does it mean? It means that if you have an image, okay, let us don't complicate it, let us keep it simple. If you have a signal, so that signal can be broken into different bases. You can have different base signals. See, it's very clear here that this signal is composed of all these signals. So for this, in mathematics also, there is something called the base vector space. So what does it mean? If I have 3-4 vectors, say v1, v2, v3, and I have some base vectors b1, b2, b3, if I can express v1 as alpha 1 b1 plus alpha 2 b2 plus alpha 3 b3, v2 also has some beta 1 b1 plus beta 2 b2 plus beta 3 b3. Same way v3 also I can express in terms of b1, b2, b3. Then I can say that this vector space is the base of those vector v1, v2, v3. That means every vector in that vector space I can represent in terms of these base vectors. So you can correlate with this. So I have here f1, f2, f3. So I can represent multiple waves in the signal domain using these 3 frequencies. That means alpha 1 f1 plus alpha 2 f2 plus alpha 3 f3 will give rise to this signal. Maybe beta 1 f1 plus beta 2 f2 plus beta 3 f3 will give rise to another signal. So that means base signal, it's different. So this is where we extend this concept to the images also. So, signal, we can see that it's a 1D frequency, one dimensional frequency, right? But in images you have frequencies in both the directions. What is frequency? Frequency is the change in amplitude with respect to time. But here you have change in amplitude with respect to x, change in amplitude with respect to y. So you have two frequency components here. So you have the frequency component along x as well as along y. So that said, so like this signal you can represent in terms of multiple base signals, and image you can represent in terms of multiple base images having base frequencies. So that means there is an f1 frequency image, there is an f2 frequency image, there is an f3 frequency image. What do you mean by frequency in an image? That's now the question. This concept, if we extend it to frequency in signals, what is frequency in signals? How? The rate at which the amplitude is varying with respect to time. Here the rate at which the pixel values are varying with respect to x and y. So in an image, where is the portion where the pixel values will vary at a very high rate? Which is that portion? What is that portion called? It's called an edge. See, the edges are the portions where you can see this one, right? So see this wall. In this you can see that all these uniform portions, the frequency is very less. Why? Because the rate at which the pixel value is changing with respect to x and y is quite less. So the moment you reach the edge, what happens? The rate at which the pixel value is changing is very high. So that said, the high frequency components in an image are the edges, and the low frequency components are the uniform surfaces. So what is high pass filter? High pass filter will only allow high frequencies to pass through. So that said, in an image, high pass filter means what? It's an edge detector. So that means it will allow only high frequencies to pass through. What's a low pass filter? It is something which will dilute those edges. It will not allow those edges to pass through. So this thing you can correlate with the concept of signals. So that said, we can extend the concept of frequency to images. There it is more of called spatial frequency, because it's change in values with respect to x and y. That means change in values with respect to the spatial location. With that spatial location, how fast it is changing. I hope it is clear. So we started with the image signal thing. Then we checked what is grayscale image, what is binary image, black and white image, and then we moved on to RGB type of images. We have seen the same Fourier transform we can also apply to images. So here you can see that like you have image based frequencies which will combine towards the actual signal. Here in images you can have image based frequencies which will give you the actual image. I hope it's clear. So the Fourier representation of a signal will have these components and their strength. So same way the Fourier representation of an image will have these components and their strength. So that said, here you can see this is having, I can represent this as one component having one sort of frequency in x and y direction. This is another component. So you have to always think that this is a two-dimensional representation. See, there you have only one dimension, one single frequency. Here you are having a pair of frequencies. That means like this, you can combine them together to give rise to different images. So this is one such image. See, this image is maybe having the size of full thing. Okay, so this is one image, this is another image, this is another image. So all these images, they combine together to give the actual image. I hope this is clear. You just have to correlate with the concept of signals to make it more clear. Always remember this diagram. It will make things more easy. See, here you have one-dimensional signals in different frequencies, which is composing, which will give rise to your actual signal. So same way, there you have two-dimensional base images, which when added together will give you the actual image. So now we come back to just want to introduce one concept of remote sensing. So far we understood images. So how we are getting images? You take a photograph, you will get the image, right? So same way, suppose if we are fitting a camera to a satellite, and the satellite is taking Earth photograph of Earth surface. See, most of us may have traveled in flight, so you know that when you are traveling on flight, when you look down, you can see the terrain. So same way, if you look down, if you fit a camera to the flight, or if you fit a camera to the satellite, what satellites will do? They will take the photograph of the Earth surface from above. So they are at a height of around 700 kilometers from the Earth's surface and are taking the Earth's surface photograph. So this is the mechanism. So you have sun. There are different types of remote sensing. For simplicity, we focus on passive remote sensing, which is like use some other source of energy. Like when you are walking in the daytime, you don't need a torch light, right? You don't need a light, but you use the sun's energy to do that. So sun is giving all this energy on all objects. It is illuminating all the objects. Then what will happen? These objects will reflect the energy. Like my red shirt was reflecting energy in the red domain. Based on the material properties, each object on the Earth's surface will absorb certain regions of the electromagnetic spectrum and will reflect certain other regions of the electromagnetic spectrum. And you have a sensor on board satellite, which is actually camera, which will capture images in all these different wavelength domains. Like I told, we have a red camera, we have a green camera, we have a blue camera. Satellite will also have all these sensors. In addition, satellite will also have sensors for other portions of the spectrum, which we cannot sense. See, we can only sense red, green and blue, but satellite can sense all the other regions of the spectra as well. So that is the advantage of having satellite images. So that said, so now we as a human being, we can only perceive 3-band images. Red, green and blue. Either you can display them as individual grayscale images or combine them as color image. That's it. But satellites can sense maybe 400 bands, 200 bands, 10 bands, 20 bands, depending on how many sensors, the capability of the sensor, it can sense. See, there are different types of sensors, how this is being split into different things. So that's beyond the scope of this talk. So we will focus on how these images are, how we are able to obtain these images. So that's it. We can have all these different spectra. So that means each spectra is one grayscale image. How much I am sampling, each of them I can have one image. So this is along the spectral direction. I hope you understood. So if I have only one image for this entire wavelength range, I have only one image. So that means I have only one camera which will receive the energy from red, green and blue. And the other case, I have 3 cameras which can separate red, green and blue. I hope it is clear. I have only one camera. I get all the energy into that one camera and I will capture a picture. But I have another camera which will separate that energy into red, green and blue. Same way I can have 400 cameras which can separate the energy coming into 400 images. So that means I am splitting this energy into different images. So how much I can split? That is called the spectral resolution of an image. That means how many bands you have and how continuous are those bands. That's called the spectral resolution. See, one thing we discussed is a radiometric resolution. That is the number of bits being used in representing one pixel. But here we are also talking about how many such bands you can have. That is called the spectral resolution of an image. So that's it. If you have more spectral resolution, what is the advantage? See, the problem with our eyes is that if I give you 2 green leaves of 2 different plants, maybe based on its color only you may not be able to identify which leaf it is, because both of them appear green to us. Is that clear, the question? See, I give 2 green leaves to you. See, based on the shape you can distinguish them. But if I ask you, based on the color only I distinguish these 2, you may not be able to sometimes, because both of them are looking same. Then if you use IR or different, another spectrum of this electromagnetic radiation, you will be able to better identify that. Why? Because although they reflect this visible spectrum equally, there may be some difference in how they are reflecting or absorbing the IR spectrum, infrared spectrum. I hope it is clear. So that means, there may be some wavelength or some wavelength of the electromagnetic spectrum which these objects will be reflecting differently, so that you are able to identify, or you are able to distinguish them. I hope it is clear. So that means you have, why actually you need different spectra or you need a high spectral resolution is that if you have a single image or a single grayscale image, if you are not splitting the energy, you may not be able to distinguish between the materials having similar properties. For example, if you take a photograph of Earth's surface, it will be something like this. So each pixel here represents one region on the ground. Each pixel here. See, always remember our initial initial diagram. So where each pixel, in this face photograph, each pixel represents one area on your face. So now here you are taking the picture of Earth's surface. So each pixel represents one area on the Earth's surface. So, and this value corresponding to that pixel corresponds to the energy coming from there. For example, if I say that it's a red image or the grayscale image corresponding to the red wavelength, the position there, it denotes how much red energy is coming from that area on the Earth's surface. I hope that is clear. So that said, you can have an image like this. So this is a picture of Earth's surface, and each pixel denotes one area on the ground. So if I say that there is another concept coming here, that's called the resolution of that satellite image, and this resolution we call it the spatial resolution, and that denotes how much area on the ground is being sensed by one pixel. That means if I take one pixel, how much area on the ground is being sensed for getting the energy for that one pixel, or it's the size of the pixel with respect to the surface. I'll clear it. 30 meter. If I say this satellite image is having 30 meter spatial resolution, it means that 30 square meter area on the ground will be represented by one pixel. If I say it's 3 meter, that means 3 square meter area on the ground is represented by one pixel. So as you have finer spatial resolution, you can actually have objects more clear. Because if I say 30 square meter is represented by one pixel, that means you can see many things on the ground will be represented by one pixel. Means you won't be able to clearly see things. But if I have 3 meter or 30 centimeter spatial resolution, we can have we can see even the people on the ground. So 30 centimeter on the ground is represented by one pixel. So that means it's very clear, you can clearly see things. So there is radiometric resolution, there is spectral resolution, there is spatial resolution, which so this particular, if I take a patch of this image, you can see the patch will be like this. We'll come to this. Before that, this is what I was talking about, the spatial resolution. That means here you can see the pixels are, the size of the pixels are known. That means this much area will correspond to one pixel. But here, smaller areas corresponding to one pixel, here still smaller areas, so that will be more clear by this image, which means that the first image is having a poor spatial resolution. Next image is having, we are improving the spatial resolution one by one, so you can see that the things are more clear here. I hope it is clear. And now, this is what I was talking about, the spectral resolution. You can see, if I have only one band, I will have only one point here. See, this is one pixel in this image. One pixel. One pixel will have 1, 2, 3, 4, 5, 6 values. Why? Because that one pixel will have one in that band, one in this band, one in this band, one in this band, one in this and one in this.